All right, everyone. Welcome to week 8, reverse engineering 2. Today, I'll be talking about more reverse engineering techniques. So first off, some announcements. Okay, there we go. We have ACM Cleanup Part 3 this Sunday after our Sunday meeting, which will be a guest speaker talk. There will be pizza. And this is an official ACM social event, so please come out for that and help us clean up the room. And the talk this Sunday will be with Ninja. It will be about healthcare data and how that relates to third-party trackers. So that's going to be super exciting as well. Be sure to come out to that. Here's the meeting flag. Go to ctf.sigpwny.com, enter that in for RE2 meeting flag. Let me know if that doesn't work. Yeah, angr here. If you don't know what angr is, by the end of today, you will know. It's a very wonderful reverse engineering tool that can help you solve a lot of challenges very easily. But it doesn't work on everything. Okay, I'm just gonna give you guys a second to type in the flag. How many R's is that? Well, you'll have to count, but it's 8. Wait, is Zoom, the Zoom screen share? Okay. All right, hopefully you guys had enough time to type that in. Just a quick table of contents what we're gonna cover today. First of all, different techniques. So these include constraint solving, symbolic execution, and instruction counting side channels. I'll explain what each of those mean in a second. And then different obfuscation techniques that you might run into, binaries that are hard to reverse and how we can get around that. So there's self-modifying code, and as well as VM obfuscation. VM is virtual machine. All right, so constraint solving. What is constraint solving? Imagine if you see this in your Ghidra output. This does not look like a very fun thing to reverse. I don't know about you, but I don't want to put that into a calculator or do that by hand. So what we can do is, first of all, we can use something called Z3 to solve these sort of constraints. So Z3 is a constraint solver. If you're at Fall CTF, this part of the presentation is going to be very similar to what I talked about for Rev. But Z3 can solve complex systems of constraints, such as something like this. I know this is not very complex, but it's very easily expandable to more complicated expressions. And Z3 will find a single solution for these system equations. So note that it finds any of the possible solutions. So even if you have multiple solutions, it will just find one of them. And this is very helpful. For example, for these, you can easily convert these into Z3, this bottom code segment. You can convert these to Z3 constraints and then feed them into the solver. But why do that manually when you can do it automatically? So there's a tool called angr, sort of skipping ahead here. But there's a tool called angr, which will automatically generate constraints from the binary itself. And this tool is pretty easy to use. You can just use the template that I've given it in the link over here. That's the link. The slides are on Discord, by the way. If you use this code template, it will automatically go through your binary and pick out the constraints based on what you want as the outputs. So in the middle of the screen there, you have simgr.explore find equals like correct in the output. So that's like what you want the program to do and what you don't want the program to do. If you specify that to angr, angr will go through the code automatically for you and pick out the constraints and find the inputs that work. So how does angr work? Well, it uses symbolic execution, which instead of executing assembly instructions one by one with concrete values, it uses these things called symbolic values. So symbolic values are like variables in math. On the right-hand side here, we have a little snippet of ARM assembly. And on the left-hand side is the constraints that angr or whatever symbolic execution engine picks out from the assembly. So doing this process, it will find, once it picks out these constraints, it can then put them into a constraint solver such as Z3, and then you will be able to find a correct solution. Okay. As I've said, one of the So I haven't said this. There's several different usages for symbolic execution. One is for solving for an input. That's pretty obvious. If your program asks you for a correct password, you can solve for that. But there's also other usages. One of those examples is automating parts of pwn challenges, such as solving for some input such that the instruction pointer gets overwritten. And then you can also do other things like solving for input such that your instruction pointer gets to a certain place in the file, or that your like an overflow happens to bypass the canary or something like that. So this is angr. Again, this is this template here is pretty generic. That means that it works for a lot of challenges out there. There's very little that you have to change. One thing I'd like to point out here is the bottom 2 lines here determine how you pass in your input to angr. So if your challenge binary accepts inputs on the command line, then you should pass it in the argv, the argv equals line. And if it accepts input in from standard in, you should pass that to standard in, which is what it's doing right now. As you can see, stdin equals symbolic flag. So that's a quick view of angr. To install, just do pip install angr. Pretty easy, straightforward. It's a Python tool. So, all right, now we'll talk about side channels. Yes.
Does this work on a Mac?
No. I'm sorry, but well, okay. So first of all, angr has to be able to run your. Well, okay. I don't know if angr needs to run your binary, but I know that angr uses certain tools under the hood that are only available on x86 machines. So if you try to run this on an M1, which is not x86, you might run into issues. So I recommend installing angr on the same operating system that you're running these binaries on. Typically, these are going to be x86 binaries. Angr may or may not work with ARM binaries. I don't know, but if you're using an ARM binary, you can probably use M1. Yeah. Any other questions? That was a good one. No? Okay. We're going to talk about side channels now. Okay, so what are side channels? Side channels are ways to get the program to leak certain information that it's not supposed to. So one of those information is the number of instructions that it executes could hint at how much work that the code is actually doing. So imagine something like this: string comp user input to flag, and then it prints correct if it's correct, and then wrong if it's wrong. So what could be wrong with this? Well, suppose you only had 1 character of the flag correct. Then it would run for a short amount of time and then immediately say it's incorrect because it detects 1 character is correct, the 2nd character is wrong. And then what if you had 3 characters of the flag correct? It would run for a longer amount of time. And then you would be able to know that, oh, this input has more of it correct, just based on the count of the number of instructions that it executes. This is dependent on the code breaking early when it's like breaking out of a comparison loop early when it detects that something is wrong, like one input is wrong. And it also matters about what order it traverses the flag. So this is really helpful for, I think, the side channel challenge on CTFD. So there are several tools for instruction counting. One of them is PIN from Intel. This is one of my favorite tools for reverse engineering. It can do a lot of things besides count instructions. Different instrumentation tools, you can count specific instructions, you can count specific loop iterations. It's a very powerful tool. And then this link is a custom PIN tool that I wrote, which is a template of sorts for writing your own PIN tools. So tools are, I should explain. So PIN tools are sort of like programs that PIN itself runs on your binary. to do certain instrumentation tasks, such as count specific instructions or do whatever you want. So these are, this is Intel pin. Installing this might be a little bit tricky, so please let us know if you have any issues with that. Is there a question?
How does instruction counting work?
Okay. How does this, well, how does instruction counting work? Well, as I've explained earlier, with something like string comp, it's going to, string comp under the hood might be implemented by something like a for loop, where it loops over all the characters of both of the strings and then breaks out of the loop if one of them is different. And then at the end, if they're all the same, it's going to return 0. But something like that would run for less instructions if less of the flag was the same compared to if more of the flag is the same. So I know I probably should have added a for loop example here, but just try to picture a for loop and think about how many times the for loop is going to run based on how many characters in each of the flag or each of the inputs are the same. So the core idea here is that side channel attacks work when when something happens that causes the program to run for longer versus shorter. And that something is related to how correct your input is, or how, or related to whatever your goal is. Okay. Now let's talk about some common obfuscation techniques that you might run into. One of them is self-modifying code. So self-modifying code, as the name suggests, is code that changes itself as it runs. So here on the left is a little bit of x86 assembly. Don't worry if you don't understand it, that's all right. But on the right there is a GDB output. As you can see, once we get to the sub instruction, the instructions immediately change from a push 5 to a syscall. So this is one example of self-modifying code. If you put this into something like Ghidra will read that you're pushing 5, and it doesn't know that it's getting modified in a certain way. So the idea with self-modifying code is that you want to run this in the debugger to see how it gets modified and look for patterns, perhaps, of what it's doing. If you try to compile this, assemble this and compile this, you will need this flag down here, the OMagic flag, to get the text segment writable. The text segment is where code is stored in a binary, and by default, it's not writable due to for security reasons. But if you just want to test self-modifying code, that's one thing you could do. Okay, any questions about this? No. Okay. All right, and then the last thing we're going to go over is VM obfuscation, virtual machine obfuscation. This is one way of making code really hard to understand by turning it into specific VM instructions, perhaps with a custom VM or something more general. But when you do this, the resulting binary, the control flow of the resulting binary will look very confusing because it will just be a VM interpreter of some sort, interpreting different instructions. The general idea with VM reversing is that you want to work your way up this, what I call an abstraction ladder. So work your way up from the VM's instructions to something higher level. Look for patterns about, look for patterns for what it's doing and try to figure out what it's doing. Usually with VM obfuscation, it's not written directly in the VM's language. I don't know if I'm being very clear with that. What I mean is that usually whoever designed the challenge started with some very high level construct and worked their way down through various compilers into a VM language. So think about how that process is done and how the reverse of that process works can help you in solving VM challenges. But usually at the end of the day, they just take a ton of time. You're gonna need to write a bunch of your own tools, and might be really frustrating, but it's gonna be very rewarding at the end when you solve it. So there's a challenge on CTFD called Hell, aptly named, which is a VM reversing challenge. All right, so that's all I have for the presentation. Go try it out for yourself. Just to recap, these are the different tools that we covered. We covered pin tool, pin, covered angr, Z3, that's how you install them with pip. And then, yeah, let me know if you have any questions. Some upcoming meetings. So next Sunday, or this Sunday, sorry, we have the guest speaker talk by Mingjia. That's the title, All Eyes on Me. Interesting title. Next Thursday, social event, TBD. Be sure to come out for that. It'll be very fun. And next Sunday, we'll have the Halloween party. So that's all I have for you guys today. Thank you very much.
Oh. Yeah.
Okay. Hello, everyone. Hello again. I'm just going to talk a little bit more about side channels just to clear up any potential confusion. So the reason that side channels work is because there might be code, as I've said earlier, there might be code that runs for less iterations or more iterations based on the input. So here we have an example program that checks your user input, that's the scanf, against the known string, SIGPwny hello. So this calls string compare. And if you look at the top, what string compare does is it iterates through each character of each of the strings one by one, and it returns -1 immediately if they are different. So imagine string B had the input AAAA, like 20 A's or something. So then the string compare would break after one iteration of the for loop. It would see that, oh, these strings are different. So it's only, the for loop itself is only going to run one time. Now, if your input was something like S and then 10 A's, and then the for loop would run 2 times before it breaks out, because the first character would be the same and it would keep running, and the second character would be different. So then it breaks out of the loop. So this way you can try characters one at a time for the first character to see which one causes the program to run for just a little bit longer. And then as you do that one by one, you'll be able to figure out what the flag is, one character at a time, starting from the first one. So at the very end, you will get something like SIGPwny hello, and that's going to take many iterations of the for loop before it returns, because many of the characters are correct. So any questions about side channels, instruction counting? No? Okay, all right, go back to challenges.